Chapter 1 Fundamentals of Thermodynamics. Section 1.1 What is thermodynamics? In the previous video, we covered the essence of thermodynamics and briefly mentioned a few thermodynamic properties such as pressure and temperature. In this video, we will show that the pressure and temperature of a gas is determined by the collective behavior of all gas particles in the system, using several example problems. So first example problem in this section 1.1.1, we'll calculate the pressure of 1 mole helium gas in a 27 liter cubic container. We'll assume the speed of every helium atom is 600 meters per second in the x, y, and z directions for easier calculation. So now let's look at this container. It has a side length of 0.3 meters. 0.3 meter to the power of 3 is 27 liters. Now let's focus on one helium atom. This helium atom is moving towards this shaded area at a speed of 600 meters per second. It's about to collide with this shaded surface area, change its direction, and then collide with the opposite surface and then get back to the original position. You will keep doing this, collide with the surface on the right hand side and then collide with the surface on the left hand side, get back to the original position, and it's going to start a new cycle of collisions. Now first, we'll calculate the time period for each collision. This particle moves at 600 meters per second in this direction, and the side length is 0.3 meters. This particle will have to travel 0.6 meters to get back to the original position. So that means it takes 1 millisecond for this particle to complete one cycle of collision. During 1 millisecond, there's one collision between this particle and this shaded area. So during a 1 second period, this helium atom may collide with this shaded surface area 1,000 times. In each collision, the momentum of this helium changes. This is because although the speed remains constant 600, the direction of the velocity of the motion of the particle changes. So you can say it changes from 600 to negative 600, or from negative 600 to positive 600. Anyway, the magnitude of the change of the velocity is 1200 meters per second. So there is some momentum change to this helium atom in each collision. And now within 1 second, there are 1,000 collisions. So we can calculate the total momentum change caused by the collisions, which is just 1,000 times the mass of helium times 1200 meters per second. Again, this 1200 meters per second is twice the speed of the helium because, again, the direction of the helium changes before and after the collision. Now we have the force calculated using this equation. Force times delta T is equal to mass times delta V. So this is from Newton's law. We just need to divide this m delta V by delta T. Within 1 second, there are 1,000 collisions times mass times the velocity change. And by the way, this is the magnitude of the velocity change and divided by delta T. And then we get this expression, mass of one helium atom times 1200 kilometers per second squared. Alright, this is just one atom. What if we have 1 mole helium atoms? We just need to take account the collective behavior of all atoms. All atoms are moving around, and then each of them is keeps colliding with this shaded area, again 1,000 times per second. So we can calculate the force by multiplying this expression by Avogadro constant. How do we multiply the mass of helium by Avogadro constant? We'll simply get the mass of 1 mole helium, which is 4 grams or 0.004 kilogram. Kilogram is the SI unit of mass. That's why we're going to use kilogram here. Therefore, the force is the mass of 1 mole helium atoms times this 1200 kilometer per second squared, we get 4,800 newtons. Remember, 1 newton is 1 kilogram meter per second squared. Now we can calculate the pressure, because pressure is the force divided by the area. We have force on top, area on the bottom. We get 53 kilopascals. This is roughly 0.5 bar. We can also calculate the temperature using ideal gas law, PV equals RT, because we have the pressure calculated, 53 kilopascal. We have the volume, 27 liters, converted to 0.027 cubic meter. And then we have the number of moles. We have the gas constant on the bottom, 8.3 joule per mole K. We can compute the temperature of the gas, 173 Kelvin. So from the speed of a helium atom, somehow we get the pressure, 53 kilopascals, and the temperature, 173 Kelvin, by looking at the collective behavior of all gas particles. Now, let's do more quantitative analysis. What if the speed of all helium atoms doubles? Let's go from 600 meter per second to 1200 meter per second. What happens to the pressure? What happens to the temperature? It's pretty simple. When the speed doubles, the momentum change of the helium due to the collision also doubles. So before, it's going from 600 to negative 600. Now it's changing from 1200 to negative 1200. Therefore, the momentum change of each collision doubles. In addition, the number of collisions per second doubles. It's just because this particle moves faster, twice the speed. That means it takes now only 0.5 millisecond to complete an entire cycle of collision. Within 1 second, there will be 2,000 collisions. The number of collisions doubles, and also the momentum change doubles. Consequently, the force exerted on this area quadruples. And since we have the same area, the pressure quadruples. Using PV equals RT, the temperature quadruples. And actually, we know that the temperature of a gas is a measure of the average kinetic energy of the gas particles. So it makes sense. The kinetic energy is proportional to V squared. Therefore, when the speed doubles, the temperature and the average kinetic energy are supposed to quadruple. For simplicity, we assume that all gas particles move at a constant speed v. So in the previous examples, 600 meters per second in each dimension. And what about the expression of the total kinetic energy of all those atoms? Well, it's pretty simple. We have n atoms. We have 3 dimensions. In each dimension, it's 1/2 mv squared. So we have this formula. And in general, the gas pressure caused by collision can be expressed this way. Pressure is force over area, and force, again, it's just delta P over delta T if you have only one single helium atom. Delta P is the magnitude of the change of the momentum of a single helium atom. But now, what if we have n such atoms? We put n here, and delta P is the momentum change. It's 2 mv rather than 1 mv due to the change of the direction. So the velocity goes from mv to negative mv. So the change, the magnitude of the change is 2 mv. What about this delta t? Delta t is the time period. So it's the amount of time it takes for a helium to collide with the shaded area and then collide to the opposite surface and then get back to the original position. It's 2L over V. So putting everything together, we get this simplified expression for pressure. The number of helium atoms is uppercase N. M is the mass of one helium atom, and then V squared. V is the speed of a helium atom in the X direction or Y direction or Z direction. On the bottom, we have V. Why do we have V? Because we have L here, we have A here. L is the side length and A is the area. A times L is the volume of the container. Alright, and also we know temperature is PV over nR for ideal gas. And then we can plug in the expression of P. P is this we're plugging in here, we get temperature. Temperature is equal to the number of helium atoms times the mass times v squared over nr. Now you can see actually temperature is proportional to this v squared. Again, when the speed doubles, temperature quadruples. What about the total kinetic energy of all particles? We have 3/2 n mv squared. N is the number of atoms. And why 3/2? This is because we have 3 dimensions. And then we have this equation that can be used to compute temperature given the speed of individual helium atoms. Again, I want to emphasize this temperature is proportional to the total kinetic energy. Temperature is proportional to this mv squared. So again, if we assume all gas particles move at a constant speed v in each dimension, we have this equation, and we can divide this equation by the number of moles. We get this equation. This is just because the number of atoms divided by the number of moles is Avogadro constant. Avogadro constant is 6 times 10 to the power 23. Now both sides further divided by the Avogadro constant, we have this 3/2 mv squared is equal to 3/2 kBt. On the left hand side, we have the kinetic energy of one individual atom. Again, 3/2 mv squared because there are 3 dimensions. In each dimension, it's 1/2 mv squared. Alright, over here we have 3/2 kBt. Kb is the Boltzmann constant. We can see from here R divided by Avogadro constant is K sub B. So we can calculate the Boltzmann constant. It's this ideal gas constant divided by this Avogadro constant. The result is 1.38 times 10 to the power of negative 23 joule per Kelvin. Now the kinetic energy of each particle is 3/2 kBt in 3 dimensions, or you can say 1/2 kBt in each dimension. Later in chemical kinetics, we can prove the average kinetic energy is 1/2 kBt by assuming a more realistic Boltzmann distribution of velocities. So in this Boltzmann distribution, the particles do not have to have the same speed. They can have a wide range of speed in each direction. Now here's another example problem. We can calculate the temperature of 1 mole helium gas in a cubic container, but this time let's just assume the average kinetic energy in each dimension is 1/2 kBt, and we're going to use this equation. So again, in each dimension the kinetic energy is 1/2 mv squared. It's also 1/2 kBt. We'll prove this actually in chemical kinetics for a wide range of distribution of speed. But now let's just use this equation. By using this equation, we can see temperature is just mv squared over kb. It's not easy to actually get the mass of a helium atom. It's just because you need to use 0.04 kilogram divided by Avogadro constant. So why don't we multiply the top and bottom by the same constant, Avogadro constant, and this m is converted to the molar mass, and this case of B is converted to ideal gas constant. So this is a lot easier. When you do numerical calculations, we have just molar mass times v squared over r. This is a molar mass of helium. Again, gram is a non-SI unit, kilogram is the SI unit of mass times v squared divided by r. We get the temperature 173 Kelvin. That's the temperature of the gas. Just based on this information, the speed of helium is 600 meters per second, and by using this equation. All right. So in general, we have this on average, the 3-dimensional kinetic energy of a gas particle is 3/2 kBt. We'll prove this in chemical kinetics, but for now we'll just use this formula, and we can see that we can compute the 3-dimensional root mean squared speed for those ideal gas particles such as helium. using this equation. Again, this is three-dimensional. That's why you see a 3 here. And Kb over lowercase m is actually this R over the molar mass. Make sure you use SI units for all three properties, R, T, and M. You'll be able to get this three-dimensional root mean square speed also in SI unit, which is meter per second. Alright, I want to show you the distribution of the three-dimensional speed over here. So if you look at this graph, there are three different temperatures: 100 Kelvin, 1200 Kelvin, and 3000 Kelvin. On the vertical axis, it says number of particles. On the horizontal axis, it says speed in meter per second. Again, this is actually three-dimensional speed. So from this graph, you can see actually we have more particles with this speed at 100 Kelvin. This is a little above 400 meter per second. When you have a higher temperature like 1200 Kelvin, we have a larger, most probable speed. So this labeled number 1, this is most probable speed. Even higher temperature, we have even higher most probable speed. What about number 2, number 3? Later we'll see. Number 2 is the so-called average speed, and this number 3 is the root mean squared speed. So root mean squared speed is over here. It's close to 600 meter per second at this low temperature, 100 Kelvin. When it's 1200 Kelvin, the root mean squared speed goes up. Again, it tells you at a higher temperature, the molecules in general move faster, but they do not have the same speed. There is a distribution of the speed.